things that we need to kind of chat about. First is just a reminder on the when you first boot up with my image, you have to do this. Sudo res pyconfig. Now, in my case, I didn't have to put in my password, but if you do, it won't display the password as you're typing it, nor does it display little asterisks. So it looks like you're not typing anything, but you are. Okay, that's just the way Linux does it. Okay, and then on advanced options, expand file system, hit that, that's it. Okay, that's the only thing you have to do after you put in my SD card image. Okay, and then reboot and you're good to go. Okay, so let's go into Python. And what I want to talk about for just to kind of get started is one of the ways in which Python is nice but also irritating. Okay, so if I declare a couple of variables in Python like a equals 2, b equals 3.5, c equals hello, right? Okay, great. Can I do the following? Yeah, okay, and it works fine. Okay, but if I look at the type of A and the type of B, they're two different classes. Okay, so A is of type int, and that makes sense because it's a whole number, and B is of type float. So how do I add an int and a float? Like, how does a computer do that, fundamentally? Yeah, it switches the two, the true int here, converts it to a float, then adds the result of, or adds that and the float b that we had already defined, and then the answer of that thing is a float. Okay, so if I do something else, like for example, reassign a to be a plus b, what is a? 5.5, but what's the type of a? It's now of class float, even though it started as class int. Okay, so now how much when you guys did 111 did you guys talk about data types? And maybe at least a little bit? Okay, so one of the things that's nice about Python is that you could just do this, right? If I defined something that was an integer and something else that was a float, and I wanted to combine them in some sort of mathematical way that, we do kind of all the time, then great. You just add them together. Python keeps track of everything. No problems whatsoever, okay? Now let's contrast that with C. All right, so let me go in here to C, and I'm going to make a new program here. So let me save it real quick. So we'll call this, data.c, nothing special. Okay, and then I need to include a couple of things, which we don't really need to worry about what those do right this instant. Okay, so if I want to, I also need a main function, so let me get that in here. And a return 0, just to keep the operating system happy. All right, if I say A equals 2 and B equals, what did I say, 3.5? Okay, you see it's already throwing an error. Okay, what's the issue? What's the problem? Yeah, I've got to define what kind of data this is, right? In Python, it just sort of naturally interpreted it and picked the obvious data type, because what else would you want 2 to be? Well, maybe you wanted it to be a string that had the character 2 in it, But if you wanted that, like, you should have done it and put it in quotes, right? Um, or, or something like that. So in C, you have to be very careful and explicitly define the data type. Okay, so in this case, what data type do I want for A? I want it to be an int, and for B, in this case, I'll just make it a float. Okay, but if I do something like float C equals A plus B, okay, doesn't look like I have an error, but if I compile this, or sorry, it wasn't hello, it was, what did I call it, data.c. Oh, I'm not in the right directory, no wonder. There we go, okay. Okay, and then I run it. Well, I didn't have it print anything out. So let me actually add that in. And I'll explain what I'm doing here in a minute. Oops, recompile, re-execute. Okay, so in this case, the C compiler was nice to us, okay? This step right here should have been illegal, okay? And the reason is you can't add an int to a float. What can you add to a float? Another float, okay? And so what the compiler has done here is basically inserted a type conversion for us so that we didn't have to worry about it. Okay, um, kind of like Python. Okay, but strictly speaking, the language, I shouldn't have been able to do this. Okay, you have to be careful about your data types. You can change data types uh, in a way. Okay, but you have to be careful with that. Okay, so let's talk, what are the data types in C? Okay, so let me start a comment section here. Oops. Okay, let's start with the numerical ones because that's the easiest. So what are the numerical data types? Well, we already said int. It's 32 bits, okay? The processors that we're dealing with here are what on the Raspberries? They're 64-bit, okay, which means that the registers can handle 64-bit arithmetic, okay? If you type int, however, it's going to default to a 32-bit integer. If you want explicitly to have a 64-bit one, then it's a long int, okay? A short for short int, is 16-bit. And there's not really a whole lot of reason that you would use that nowadays. That's more of a sort of historical artifact. Okay, so if we go back to the early 1980s, the desktop computers that people bought, like an Apple II or a Commodore or an early IBM PC, were 8-bit processors. Okay, not too much long after that, later PCs, but still 1980s era, had 16-bit processors. Okay, and so what a short or a long is kind of depends on what time period you're looking at and which compiler you're looking at. But since we're using modern hardware um, right now, um, long int is 64-bit, short is 16, int is 32. Okay. It used to be the case that if you wanted a 64-bit, you had to type long int, but you don't have to anymore with a modern compiler. Okay. Now we might want to actually deal with 8-bit arithmetic. And there is a way to do that, but it's car. Okay. Now, the reason for this may seem like, wait a minute, car should stand for character, right? Um, like a letter or something. And the reason for this is, well, how is text encoded? Or how was it coded back in, say, the 80s? Hmm? It's an ASCII. Okay. So, what is ASCII? I forget exactly what it stands for. ASCII. Okay. ASCII is an 8-bit standard for assigning a number to printable and also non-printable characters. Okay. So last time when we were looking at something and I did a hex dump and I was like, oh, here's the percent sign right there and here's the whatever, right? I was knew that those were the ASCII codes associated with it. Okay. So that's an 8-bit scheme. Well, early microprocessors that would be on your desk were also 8 bits, and so characters and 8-bit integers really are the same data type. They're just 8-bit numbers. Okay, and so we just call it car for short, even if it has nothing to do with like letters. Okay, we still call it a car. Okay, now, do you ever could you theoretically ever need to use an integer larger than a 64-bit one? In high performance or scientific computing, maybe, um, but there is no hardware support for that really on the ARM. Okay, that's kind of specialized stuff that you would have to do in another manner. Okay, we'll talk about how you do 128-bit arithmetic later because it's fun. Okay, so those are all the numerical data types that we might need. Okay, um, and the other data types that we might need would be, say, something like a string. Okay, we'll talk about strings a little bit more later, but what really is a string? Okay, so like back in Python, if I just define a string, what really is it? I mean, I put some stuff in quotes, and okay, great, I've got a string. Jaden, what do you think? Yeah, it's an array of characters. Okay. In the same way that you could have arrays of numbers, you could have arrays of characters. Yeah. Okay. And so a string is really just an array of characters. We'll talk about arrays in a little bit. Oh, I forgot. These are all the integer data types. What did I forget? All the floating point data types. Okay. So on these modern ARM processors, you have a float. Float is a 32-bit floating point number, and we'll talk about the standard under which these are encoded, um, which is IEEE 754, in case you were curious. We'll talk about that later. What about if you want a 64-bit integer, or excuse me, a floating point number? So it's more precise. What's that called? Anybody happen to know? No, it's okay. It's called a double. Okay. Um, and uh, there are, in some compilers, you can define a 16-bit floating point number called a half precision, right? So the idea is 32-bit single precision, 64-bit is double precision, 16-bit would be half precision. How many of you guys took CS-101 with me? Right? Remember when we did the floating point and we did it in the 8 bits? That would technically be quarter precision. Nobody in their right mind would ever actually use that, but it was nice for teaching because it was short. Okay, so yeah, 32-bit, 64-bit. There are some instances where you use 16-bit floats in machine learning and a few things, but that's kind of a specialized application. Um, it does maybe bear mentioning here, just so that we're clear. Um, how big can a 64-bit integer be? What's the largest 64-bit integer? Okay, so it's, huh? Oh, it's way bigger. 2 to the 63 minus 1. Okay, and the reason it's 2 to the 63 and not 2 to the 64 is because we're including negatives also. Okay, so half of the numbers encoded are negative, the other half are positive, and 0 being right in the middle is why I have to subtract 1. Okay, so let's go to our favorite little handy dandy Wolfram Alpha to compute this. All right, so 2 to the 63 minus 1. It's this number. That's very large. Yeah, would you guys agree? Okay, so that's the largest number that you can encode in uh, as a signed integer in 64 bits. Now, for comparison, let's do a 32-bit. If you include negatives, this is the biggest you can get, 2 point whatever billion. Do you think we might run into situations where we could exceed this number in normal computing life? Oh yeah, definitely. This number was, by the way, the one that broke YouTube. The Gangnam Style music video. What happens when it had this many plays and somebody watched the video? It added up and it rolled back around and it had negative play count and it broke YouTube. And so they said, okay, we'll do it with the 64 bits. And so now the maximum uh, play count that the Gangnam Style or any other video can have is this. And how many is this? Each person on the planet would have to watch the video 1.1 billion times for it to break YouTube again. Yeah. Well, there's what, 19 of you in the class? Get to it, right? Well, okay. Let's say that that's a second that it takes you to watch it, right? It would take you 10 to the 10th years to watch the video that many times, assuming that each play was a single second. Okay, so you're going to be long dead before that happens. Sorry to break it to you. Okay, so 64 bits are incredibly large numbers. And the precision you can get with 64-bit floating point numbers is pretty astounding, okay? Now, here's a good question. How many bits does NASA use for interplanetary computations? Like, we want to send, well, the Artemis launch got scrubbed yesterday morning because of a fuel leak. Tends to be bad. If we want to put a spacecraft in orbit of the moon, right, there's a lot of computers that goes into that. How precise do they do it? Yeah, it's 64-bit. Okay, and in fact, so pi to 60 using a 64-bit float is precise enough that if you use that to send something, a space object, to the orbit of Pluto, that's the rounding error is being off by an inch by the time you get out to Pluto. Not really a big deal to be off by an inch when you go all that distance, right? So 64 bits is actually incredibly precise. And in fact, there's a really handy, um, website that I found uh, that so it's called Float Toy. You're going to get a bunch of ridiculous um, things, but you can see here. Here's pi to looks like it's maybe 15 decimal digits. That's its encoding as a 64-bit floating point number. and that's good enough for NASA, so it ought to be good enough for us. Okay. Right, okay. All right, so back to here. So we've got the numeric data types, and then we need to talk later about like strings and other things like that, okay? All right, so type conversion is something that the compiler here was nice and did for us, and I'm actually a little surprised it didn't give us even a warning for that. It just let us do it, okay? Because strictly speaking, we shouldn't have been able to do that, okay? And we can actually see, for example, if let me do this. Okay, if I look at the assembly for it, then this command right here is where it did the type conversion. Okay. And did we ever explicitly say to do the type conversion? No, the compiler did that for us. Okay, but there is the explicit type conversion instruction in the assembly. Okay, huh? SCVTF, signed convert to float. So we took a signed integer and converted to a float, and there's a machine instruction to do that. Okay. Um, yeah. So anyway, all right. So let's go back to here. Let's also talk. I mean, this will relate a little bit to strings. Okay. How did I make this thing print the result of this computation? Okay. I used a function called printf. The F stands for formatted. Okay. So I'm printing some formatted stuff. Okay. You have to give printf at least one operand. And that thing is called a format string. The format string is going to be composed of two things, some text if you want, okay, but also special character symbols for what kind of information you're printing. So for example, what kind of data is the number C that was the result of that addition? It was a float, okay? I want to print a floating point number. And so I have to put a %f to signify, hey, I'm going to pass you a float number and I want you to put it where the %f is in the string. Okay, so the printf function will read this and say, oh, I see a %f, and I also just got passed a floating point number. So where I see the %f in the string, I'm just going to plop that floating point number there. Okay, and I could put basically as many of these things as I wanted. So for example, let's just put it in a second time. Okay, and then I have to pass the floating point number a second time. Okay, all right, so let me recompile this and run it, and there we go. Okay, so in this case, I was passing the same number to replace in both spots. It doesn't have to be, obviously. It could be anything that I want to print there. Um, and if I want to print integers or something else, then instead of %f, I have to replace it with %i, for example, for an integer, or percent something else for something else. Yes. No. Okay. So good question. All right. So Julius's question is, wait a minute, what's this percent thing? Because what does the percent thing mean in Python? Yeah, you do it when you're doing modular arithmetic. Okay. So like, what's 6% 3 or something? 0, because the remainder is 0, right? Um, so no, it is not that. Okay. Now there's two reasons that I know that it's not that. One is I just know it's not that. The other is because I'm inside a string. right? And you don't do computations inside a string. Okay. Now, that said, if I wanted to do sort of those modular arithmetic kind of computations, those would be taking place kind of like I did this addition, not inside a string. Okay. So in that scope kind of thing, I know that I'm not dealing with. I don't mean to do some sort of arithmetic on the variable called f. Okay. And for that matter, have I defined a variable called f? Not here. Okay. Yeah, so that's how you know that it's not that. Okay. Um, and okay, so good question there. Couple of things about this. Notice how many digits did it print after the decimal point? 6. Okay, that's the default. There is a way to restrict and have it print more or fewer as you see fit. That's not really important for right this instant, but yeah, you can restrict that as you want, and you can mix any data that you want here. So, for example, if I wanted to print um, if I wanted to print the value of a, which is an integer, I could certainly do that also. Not I, it should be a. Okay, and it'll print that for me also. No big deal. Okay, but what did I have to change in order to do that? Yeah, so right here in my formatting string, I had to say, well, what kind of data is the variable that I want to plop in that location? It's an integer, okay? And so the format character or little code that I need is %i, I for integer, okay? Okay, no. Well, two reasons. One is because I also passed it A instead of C. So, okay, so you see after my format string, I have here two variables that I'm passing this function. So I'm really passing printf three things, a format string and two variables. Yes? What's the first variable? C, which is a float. And what's the second variable? A, which is an int. And you have to pass those in exactly the same order as you do those special characters. Okay, so if what did I pass first? A float, because that's what's first in the format string, and the integer is second. If I reverse those, it's going to be all screwed up. Okay, yeah. Yes, yeah. The backslash end is just makes it so it basically hits enter, right? Um, we'll talk more about the backslash stuff later. That's called an escape character, and backslash n stands for new line. Um, we'll talk about that later. Okay. Um, okay, but I have to. So my point here is that I have to pass the variables in the same order that they appear in my format string. Okay, and in this case, I just arbitrarily chose float first, int second. Okay, maybe you want int first, float second. Depends on what you're printing. Okay. Um, yeah. Good. Okay. So, um, if all you're doing is printing a single string and you're not doing any of this replacement of data, then you can just use put s, that function. But if you want to print formatted data like I did here, you have to use printf. Okay. And we'll be using printf just oodles throughout the semester, even when we're in assembly. So you have to use printf if you're printing formatted data. If all you're doing is dumping a string to the screen, you can use put s. You can also use printf, but you don't have to. Okay, it'll do either. Okay. Um, Okay, so that's sort of the numerical data types. What questions do we have up until now? Yes. Mhm. So, for example, change this to percent %I. Okay. What else? Any other changes? Hmm. Yes. In the order that you give them, right? So, for example, um, here, right, it printed new first and A second because that was the order I specified. If I reverse this, prints them in the other order. Okay, they're both integers, right? But the order that I gave them to it is how it knows which one to put where. Okay, um, and that order is a really technical thing, which we'll talk about in glorious detail later. How it actually knows what the order is. But yeah, like I said, we'll get there. Okay. Um, Now, there are lots of these format codes, okay, and we don't have to really memorize all of them right this instant, but let's just take a couple of the other ones. So, for example, a double. How would I present a double uh, here? What would be logical? A D, okay, that would be logical, right? All right, so let me define a double. Um, let's say I can't use D. Okay, do that. And then let's go here and let's say the double oops, quotes and then big float. Yeah. Uh, that basically just keeps the operating system happy. Uh, so Linux and Windows, I'm sure, does this too, but maybe in a slightly different way. Um, when a program terminates, it returns an integer to the operating system, and that integer gets used basically for, hey, did the program terminate completely incorrectly, or did it terminate with some sort of error? And the convention is that exit status 0 means, yep, everything was fine. It quit just fine. So that's just, we don't really have to have that, but it's good habit. Okay. All right. But what happened here? The double is negative 49. Wait a minute. That's definitely not what I typed here, is it? Okay. So the reason that this happened is because %D is not the code for float. It's for, it's another way of saying decimal or integer. Okay. Um, so that's not the one we want. And let's just, for sake of handy dandy reference, if I could spell character correctly, right? How many H's are in there? Okay. I think we can probably trust IBM here. Um, all right. So where's the list here? Here we go. All right. So float is this one. And Okay, this must be some weird compiler of theirs. I'm actually blanking on what it is for double. Oh, LF. No, it's not LF. It's huh. No, because that's integer. All right, whatever. I'll look it up. I don't remember. It's not really important for right this instant. But the salient point here is that what it did is it took the data, okay, the 64-bit number, and it treated it as if it were an integer for printing. Okay, and so under the hood, what's happened is a double precision number is just 64 bits of binary stuff in memory. And it took those 64 bits and pretended that they represented an integer rather than a float and just dumped whatever to the screen. Okay, which just so happens to be that. Okay, because let me actually change this, and instead of big float, let me go back and do, say, the number a, right? So, which was an integer, to be clear, right? Or sorry, the number. Let's change that so we know what we're seeing. Oops, the number is okay. So %d and %i basically look the same way. All right, let me change this, by the way, to %x. Okay, it doesn't look any different. Let me change the number. Give me a bigger number. 274. Thank you for not saying the number I'm sure that everybody in the room was thinking. Mm-hmm. Nope. It's a float, or sorry, an int, which is 32 bits. So 256 is the limit for an 8-bit thing. We're nowhere near the limit for a 32-bit int. I typed in 274 and I got 112. What on earth could be going on there? And no, there's not like a demon in my computer that's possessed it, and we need to go get Dr. Blix to like perform an exorcism. It was completely logical why this happened. Hmm? I, I don't know. Yeah, maybe he does, but he, yeah, but he teaches Eastern religion stuff, so I don't know. He could issue a fatwa against my computer. Maybe that would work instead, right? Okay, so what did I change here? Yeah, %x. Does that remind anybody of anything? It's hexadecimal. %x takes that number but displays it in hexadecimal instead of decimal. Okay, so let's make sure that this adds up. How do I convert 112, or excuse me, 112 in hexadecimal into a decimal number? Well, I'd have to do 1 times 256 plus 1 times 16 plus 2. Is that 274? What's 256 plus 64? Um, or sorry, 256 plus 16. 272 plus 4 is, or sorry, plus 2 is. Ding, 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 ding. Tell him what he's won, Alex. A new car. No? From like old game shows? Okay. All right. So it's just in hexadecimal. Now, as such, one of the things that I like to do anytime I'm printing stuff in hex is I put 0x in front of it. Okay. And that way I know that it's in hexadecimal instead of decimal. Okay, and that just saves me from going crazy. Okay, so to be clear, I'm still printing an integer. I've just changed the format under which I'm printing it. Right, the number is still 274. It's just represented in hexadecimal instead of decimal. Okay, now, how many of you guys, those of you who did CS-101 back in the day, I know you know hexadecimal. Uh, those of you who did not do CS-101, is hexadecimal like, what is this? You've never seen it before in your life? Yeah? Okay. So, how many fingers do you have on your hand? You have 10. Imagine that you live on a planet where you have 8 fingers on each hand, 8 on the left and 8 on the right. Okay? How would you count if you had 16 fingers? You'd count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. There's 15. Okay? So, because we started counting with 0. Okay? And so then what if I wrote the number 1, 0? What does this really mean in hexadecimal? 1 times 16 plus 1 times 1 is, or sorry, 0, is 16, okay? So I'm going to put a subscript here of hex or 10 just so that we know what we're talking about, okay? So it's just like regular arithmetic, except the base is 16 instead of 10. Just imagine you have 16 fingers, okay? How does binary work? Imagine you have only 2 fingers, okay, and I can come around with a knife or a sword or get my batleth and, you know, chop off all your fingers so that, Patrick, I'm telling the internet live right now that I'm going to chop off everybody's fingers, right? Um, so, yeah, okay, so hexadecimal, we're going to have to get very comfortable with that notation because uh, when we start looking at like memory and locations in memory and stuff, those are all going to be encoded in hexadecimal. Okay, so we just got to get used to it now. Okay, is that okay? Okay. So there's lots of these format codes, and at some point I had a list handy. I don't remember where I put it. I'll find it and put it on Canvas, right? These are the kinds of things you just look them up. But the biggies are, of course, I for integer, X for integer and hex, LI for 64-bit integer, LX for 64-bit integer and hex, and then F and whatever the double one is, which I'm blanking on at the moment. It's something you wouldn't expect because it's not D. It's like G or something. I don't remember. Okay. Or maybe it is LF. Oh, no, 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 no. Okay. Sorry. I remember. Um, let me change this back to a float. You guys are going to love this. Oops. The quote. Thank you. Oops. Oh, and it's 277.5 because I redefined what A was, so the sum is different. Okay, great. But let me actually go in. And let me have it output. Oops, I meant to do this. That there. Okay. Don't panic as to what these 4 lines mean, but this is, I always forget this. %F actually is the 64-bit double. Okay, so there's actually no way to print a 32-bit single precision floating point number. What you do is you convert the 32-bit to a 64-bit number and then print it. Okay, does that seem a little whack? Maybe? Okay, I'm not sure why it's like that, at least on ARM implementations of C, but it is. Okay, so what happened is this floating point number got converted from a single to a double, and then printf got called. Okay, so yeah, so that answers that question. Okay, which, yeah, sorry, I forgot about that. Okay, now, like I said, don't panic as to what those instructions mean, because this is all assembly and we'll get there. But that's what's internally happening, is we told it really to print a 64-bit double. Okay, and the compiler handled the conversion for us, which was nice. Okay, good. All right, so that's sort of the basics of kind of printing and stuff for now. Let's go back to this though, and well, what would be, if I can print some formatted data, should I be able to print like lots of formatted data? Sure, like if I wanted to make a table of numbers, for example, then what would I need to do to produce a table? I mean, I need to compute a bunch of crap. Okay, great. But then how should I think about generating that table? Huh? Yeah, some sort of order. Okay, but do I want to have to type printf like 16 times or something? No, what's that code for? Like if I don't want to type something 16 times, but I want to do it 16 times, let's talk about loops, right? Okay, so what are the fundamental control structures that you need in order to do programming? You need loops and, well, functions, yes. Okay, we'll get to those. And also conditionals, right? You need to be able to do if then or if then else kind of constructions, okay? And to do a loop, you really have to do an if then kind of construction. It's built into the loop, right? Because how do you know when the loop is supposed to finish? When you hit some sort of number, right? So in Python, how did you do this? You'd say something like for I in range, blah, 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 okay? And then it would do, however many. Well, what it's doing, right, is I is being updated by 1 each time you loop. And when I hits that max number, whatever you specified, then, okay, I know I need to terminate the loop and I'm finished. Okay, so let's look at how loops are done in here, how conditionals are done in here, and how functions are done in here, okay, to get cracking. We? Okay. So let me start a new project. Oops. Let me call it control for control structures. Okay. Let me close those. Come in here and new file. Oops, that is not the button I wanted to hit. New file, text file. Okay, and let me save this as programming control, and I'll call it control. Oops. Okay, so like before, need a couple of headers. Oops. Okay, while I'm right here, just to make sure that we're clear about one thing. So in Python, how did you know what the nesting structure of your code was? Just purely on indentation. okay? Now, in C, how do you know what your nesting structure is? The curly braces, okay? We often also indent things because it makes it easier to read, but that is not required by the language. That's just a human thing, okay? So be careful with your curly braces. This is why, by the way, you do not program after 12 midnight, because at 3 in the morning, you will never find the missing curly brace, okay? Ever. Just go to bed. Right, Patrick? Yeah. Okay. So yeah, but I would encourage you to still tab in the exact same pattern that you did when you were in doing things in Python, just because it makes things more readable. But the compiler just ignores all the tabbing. All it's looking for are the curly braces. Okay. Um, this, by the way, is one reason that Python made the structure purely based on tabbing, because it was like, well, everybody already does it anyway, and the curly braces drive everybody crazy. So why don't we just dispense with the curly braces, right? And it sure made your lives easier, didn't it? Okay, but yeah. Okay, um, so what kind of control structures do we want to have? Well, we need if then else, and we need loops of some sort. Okay, so let's just define a couple of simple variables. Okay, and what data type should this be? Let's make it, say, an integer. Okay, and we could do something like if a is less than 5, oops, I need semicolon, which, by the way, this is another thing about Python that you didn't have to worry about. Pretty much every instruction in C is going to have a semicolon at the end of it, and if you're missing that, then it's going to throw an error. Okay. In Python, you didn't have to worry about this, but C's picky. Okay. So we'll do that, and we could also do puts. Oops, something like this. Okay. So what should happen if I run this? Yeah, it should print A is less than 5. Okay, great. And let me change the value of A to something else. Yes. Not entirely. If all I want to do is print a string, not formatted data, then I can just use puts. But if I want to print formatted data where there's a string and I'm plopping in numbers, then I have to use printf. I can change these to printf without consequence. Same thing. Okay. With the exception of uh, looked like puts actually did a double line break, which is interesting. So okay, so I've got if then constructions and also if then else. Is the else required here? Do I have to have an else in an if construction? No, I can. I don't have to. It just depends on what I'm doing. Okay. All right. So there's conditionals. Um, and then what goes inside the parentheses here? That's the actual condition, right? So what kind of condition is inside the parentheses? Okay, so I typed A is less than 5, right? What kind of thing is that? Hmm? Right, it's a Boolean expression. It's evaluated to either true or false, right? A is either less than 5 or it isn't. Okay, so any Boolean expression that I might want, I can put there in that inside the parentheses. Okay, and in this case, that Boolean expression is really simple. Being less than 5 or not is pretty easy. Okay, but what about if I wanted to have more exotic conditions? Okay, in Python, how would you do this? Like, what about if I wanted to say, all right, if A is less than 5 and B is greater than 7? You type it literally like that, A less than 5 and the word and B greater than 7 or whatever it is, okay? So let me just throw in another variable here for posterity, and let's say int B is 9, and I could do something like, okay, like this. Okay, two things that, and this is certainly true in Python also, is I try to be very careful about making sure that the entire Boolean expression is in its own set of parentheses, and any sub-expressions are also in their own set of parentheses, because sometimes Python interpreters get picky about that. It's also just makes it more readable, okay? In Python, what would I have put there instead of the double ampersand? Literally the word and, okay? In C, it's not that, okay? Double ampersand means and. What do you think or is? It's double vertical bars, okay? So, and that's the key just above the enter key, but with shift pressed, okay? So double vertical bars is or. All right, so if we've got and or, what's the last one that we might need? Not, okay? And that one is, I'm going to put an extra set of parentheses just to be picky, is an exclamation mark, okay? All right, so let's parse this and make sure that we actually get the correct answer. All right, so the if part printed, let's make sure that that's should have printed. Okay, what are the values of A and B? What's A? 6. Is that less than 5? No. What is B? Is that greater than 7? Yes. But what's in front of that? So that's now false. Okay, so we have false or false is false, and therefore what printed? The else case. Okay, which, yeah. Okay, so does that make sense? The logic there? And I know it's 9 in the morning, and that means it's too early for doing Boolean logic, but c'est la vie, right? Okay, so these expressions can be as big and complicated as you want. You can also do case switches where, like, let's say that you have 12 options, like you're making a menu program or something. You can do those. We don't really need to deal with that now, but yeah, okay. All right, does that make sense? Yeah. All right, so let's go down and let's do one more if condition. How do I check equality? Double equals, okay? Okay, so let me run that. Okay, now, why did it not print anything there? Is A equal to 3? No, and I also did not provide it with an else case. So this part just got skipped over entirely. Okay, that's fine. So what's the difference between single equals and double equals? Yeah, single equals assigns, and double equals is a Boolean expression checking if two things are equal. Okay, so if I say a equals 3, that's setting the value of a is now 3. If I say a double equals 3, I'm asking, hey, is it the case that the number a is equal to 3? Yes or no? Right? So those are the distinctions there. Okay, does that make sense? Okay. If I wanted to say not equals, I can just do exclamation mark and a single equal. You don't have to put 2 in that case. Yeah, okay. Why did I not have to put int in front of a here? Because it's already defined. I already defined it up here. I was just changing its value. Okay, so you only have to put the type of data the very first time you declare it, not as you change it. Okay, so now if we run this, since we redefined a to be 3, it should print that second thing, and it does. Okay, so we're good. Okay, so does that make sense? Yeah? Okay, so if we've got conditionals, what else could we do here? Yeah, sure. Data type? Okay, so for example, something like this, which we could totally do in Python, right? Oh, did I save it? Okay, should that have happened? No, right? So why? Because what did I do when I said, when I redefined A? So in fact, why don't we do this right here? Let's do printf. Um, yeah, well, so I added this right here, okay, but it printed 0, but clearly our number is not actually 0, right? Uh, it's because I passed it a float. If I pass it an integer, right? So the reason that this happened is um, 3 as an integer, 32-bit integer, is 32 digits or 32 bits, right? Like so. And that, if you take that number and treat it as if it's a floating point thing, then it's such a small number that the decimals would be so far off to the right that they got truncated, right? So that's why it looked like it printed 0 even though it wasn't. Okay, so, but the other thing here is it's saying, wait a minute, it it's as if it thinks 3.5 is equal to 3. Okay, is 3.5 equal to 3? No. Okay, and the reason that this is happening is because we're being sloppy with the variable types. Okay, so that's bad. Okay, don't do that. Okay, so you, in general, want to avoid changing the type of a variable uh, if you can. Okay, and if you need to, so say for example, I need to convert the integer a to a float. Let me make a new variable b and call b that converted value, right? That's a much safer way to go because then we're not going to get into weird logic where you're like, wait a minute, this is not actually equal to 3. Um, okay, so yeah, so redefining variable types is bad generally. Okay. It is possible to do it, um, And it is possible to convert things from one type of data to another, but the better practice would be to use a new variable for that converted value rather than just converting the original thing. Um, yeah, okay. And there are good reasons why you would want to do that. So, for example, my favorite algorithm, well, one of my favorite algorithms, actually, that sort of dynamic redefining of things um, is the entire trick. Okay. So, how many of you guys ever played Quake 3 back in the day? So, when they released the source code, um, this appeared in it. Okay, so where's the funny part? Yeah. Okay. Um, so, yeah. So that comment right there. This is actually John Carmack wrote this code. And what it's doing is it's taking a number, okay, which is a float. It's pretending temporarily that it's an integer, doing some arithmetic, and converting the result back to a float. Now, why you would ever want to do this is that's why this algorithm is so cool, right? Because you look at it and you're like, well, right? But there's a really good reason why you do this. And that would take me about 2 hours to explain because I'd first have to explain floating point formats. Um, and then I'd have to give the explanation as to why that single line of code does what it does. Okay. Okay. Huh? Yes, that's why the comment. Okay. Anyway, so so yeah, doing variable conversion is useful. This is maybe an esoteric example, but it is definitely used. Okay. All right. So let's go back to yeah. Let's get rid of this business because we don't need that anymore. Okay. So we did conditionals, Boolean expressions. What else do we need to talk real quick? Loops. Okay. What kind of loops are there? For loops, while loops, and strictly speaking, do while loops. Okay. What's the difference between a while loop and a do while loop? And not every language has all of these, but well, the difference between a while loop and a do while loop is when you check the condition. So a while loop, you check the condition before you start executing the loop body. So it's possible that a while loop runs no times at all. A do while loop, you check the condition at the end. So at minimum, a do while loop must run once. And then a for loop is sort of a specific instance of a while loop where you check the condition at the beginning, but you're also iterating over some counting variable to do something a specific number of times. Okay. So in Python, how did you do a for loop? Yeah, you did for something in range, something, something. Okay. It looks a lot like that here. Okay. And okay, so here you need to specify three things. Okay. You need to specify the counting variable and its initial value. And because it's a variable in C, you also need to specify its data type. For loops, it's basically always an integer because why else would you count any other way? Okay, you need to have a Boolean expression that determines when you stop this loop. Okay, so I continue looping if I is less than 5 and otherwise I quit. And then the final thing I need to specify, and you didn't have to do this in Python, was how should I change each time you go through the loop? Okay, what's the default in Python? If you said for I in range 0 to 7, it would count up starting at 0 until it gets to 6, but it would count up by ones. Did you ever say to count up by ones? No, that was the default. If you wanted to count up by twos, could you? Yes, how would you have done that? You would have said for I in range 0, 7, 2. Okay. In C, you must specify how the counting variable changes each time you do the loop body. And the vast majority of times you count up by ones, right? And the shorthand for this is I++. Okay, and you guys have seen the plus plus and minus minus operators. Yeah? Question? No? Okay. Yeah, so you've got those operators are still there, right? Okay, so how many times should this loop body execute the way I've written it? Careful. 5, 0 through 4. Okay, so let me just print the character, or excuse me, print the number I. Okay, and so how many times did the loop body execute? 5 times from 0 to 4, right? And that's only because I put a less than there instead of less than or equal to, right? This is one of the things that I really hate about Python is that when you say for I in range 0 to 7, 0 is included, but 7 isn't. And I think that's kind of confusing. So in some sense, I like the way C does it better because you're saying explicitly, do I want to stop when I'm less than 5 or less than or equal to or something else, right? I've got full control over that. There's that part of the loop construction in Python makes me want to fly and go punch Guido von Rossum, who created Python. Yeah. No, I just didn't make that name up out of thin air, right? I'm just going to fly to a foreign country and punch a random person for something he had nothing to do with, right? I mean, that's, yeah, why not? Which is essentially American foreign policy, right? Let me just go bomb somebody for, okay, question? Okay, what would happen if I put greater than 5? Okay, um, the, so good question, right? What do you guys think is going to happen? It doesn't do it at all, okay? And the reason is, before it executes the loop body, it's going to check, is I greater than 5? And that's false, because I was initialized to be 0. And so that's not true. And so I'm not going to do the loop body. Done, right? So this demonstrates, by the way, that the condition is checked before the loop body is executed, not after. Yeah. I equal to 5? Or if I put I equal to 5 here. Okay, so if I did this, okay, so say 6. Yes. All right, so Min's question is, will this run infinitely? And yes, it's exactly what's going to happen. No, it'll just keep running until it overflows. Okay. Yeah, 32-bit. Right. Yeah, it would keep running until it overflowed, which would take until 2 point whatever billion. So yeah. Yes. Okay. So you've got your C code. Okay. So how do you create an executable file? GCC, then you type the name of your C file, or files if there's more than one, -O, and then the name that you want your executable to be. Okay, so in this case, control.c was my source code and just control was my binary. The control is the binary. That's what I execute with /control. Okay, and so what do I want you guys to turn in? For basically every assignment, you're going to turn in all source code, which in this case is only a single file, and your executable code, which is also a single file. And then you guys know how to zip files together, right? Yeah, that's not rocket science. Huh? No. Just pick it. Well, okay. If you do it in the graphical file browser, you just select them and right click and hit compress, and then it will ask you. So let me just show you that real quick so we're all on the same page. All right, so let's say I wanted to turn this in from my control thing. I would select these two files, I'd right click and I'd hit compress. Okay, I decide what I want to name my compressed file and what format I want to compress it in. Okay, so if I come down here to archive type, you have the following options. Okay, 7-zip is fine, tar is fine, tar.gzip is fine. I don't really care. I've told Canvas to just give it to me, right? But yeah, that's how you would compress them. Okay, make sense? All right. Well, we will quit for the day, and I will see you guys on Thursday.